We left off last time talking about solving inequalities that involve quadratics. And, I mean, like, you know the overall plan, right? Step one, solve the equality. That tells you, like, some endpoints. And then, depending on what those endpoints look like, you check some sample points, or you think about what the graph should look like, and that tells you what the solution to the inequality should be. And maybe the general flowchart, you want to solve an inequality. Oh gosh, step one, solve the equality. Since it's a quadratic, there will be one of three buckets you'll be in. Either there will be two solutions, there will be only one solution, or there will be no solutions. If there are two solutions, then those are like the endpoints of your intervals that solve the inequality. So your options are the different types of intervals that have those endpoints. Check some sample points, or think about the graph to decide which. If there's only one solution, then that's your endpoint. And then decide on the intervals with those endpoints, which ones solve the inequality, to decide what the solution is. If equality has no solutions, that doesn't mean the inequality has no solutions. The solutions could either be nothing or everything, as we saw last time. So I want to do one last thing with this idea before we do something different. I want to think about domains. Domains of functions involving square roots in particular. So here is one f of x equals square root of 1 minus x squared. And we'll double check with the graph at the end. But let's remember how you think about domains of functions. To compute the domain of a function, you just ask yourself, the ingredients here, what things aren't allowed? And then you make sure to forbid those, you write down what that means, and then maybe there's some solving to do. So let's just think one ingredient at a time. So, I see an x squared. Is there any number you cannot square? Nope, you can square anything. Now you see a 1 minus. Is there anything you can't do 1 minus to? Nope. Might get big and negative, but whatever. Square roots. Is there anything you cannot take the square root of?
Negative numbers.
Negative numbers are bad. So, if you see a function which has a square root, negative under square root is bad. So I need to avoid negatives being underneath that square root. So there's like an inequality I need to solve, right? The stuff under the square root has to be non-negative, so that's bigger than or equal to 0. So we need to solve 1 minus x squared bigger than or equal to 0. That looks like a reasonably easy inequality to solve. Yeah. And if you like, you can follow the algorithm that's on the previous page. So step one, solve equality. So go ahead and solve that. Tell me what the solutions to equality are. Yeah.
Should be root back, or root 1 minus x squared.
Ooh, so that certainly should be bigger than or equal to 0, because the square root of anything is bigger than or equal to 0. The stuff under the square root, I need to make sure cannot be negative in order for the stuff to be defined. So I do mean to be leaving off the square root there. So once you solve that equation, let me know what the endpoints you get are.
X equals -1 and x equals 1.
Right here, x equals plus and minus 1. That agree? Cool. Any call for me to do it? Cool. I'm not going to though. Instead, you're going to tell me how you solved it. What did you do to get that?
What did I do?
Yeah.
I subtracted a 1 from both sides.
Cool. Alright, so since there's only one x, I don't need to worry about doing anything fancy like factoring or quadratic formula. I can just get x on its own. So do that, minus x squared equals minus 1. What next?
Divide by -1.
Divide by -1. That'll cancel the negative signs. Next.
And you take the root of both sides.
Take the square root of both sides. Cool. And whenever you undo a square with a square root, a plus or minus sign appears. And what's the square root of 1?
1.
Groovy. What are the other things that could have been done? Let's see, how many people like factor on the complicated side? Cool. Got the same answers? Nice. How many people use the quadratic formula? Okay. You could have. Alright, so that means that I know that the solution to this thing, the endpoints of the domain will be plus or minus 1. So, I think here's the game to play. There's -1, 0. There's 1, 0. Let's sketch the graph of y equals 1 minus x squared. Upward opening to y below or downward? Downward, so it's got to do something like that. And remember, I want to know when is this thing bigger than or equal to 0. So, bigger than or equal to 0 between those endpoints or beyond? Between. Cool. So, alright, so that's enough, right? The domain is given by solving this inequality. We now have the solution to this inequality. It's the interval from -1 to +1. Include the endpoints or exclude? Include. Why include?
If you plug in 0, it's not, or it's still gives out.
Yeah. When you plug in 0 to a square root. So the thing under the square root is allowed to be 0. So there's a bigger than or equal to. If I plug in -1, this is 0, square root of 0 is 0. And same thing with +1. Feel pretty good? And let's double check this by using the fact that you can read off the domain from a graph. Square root 1 minus x squared. Oh cool, the graph looks like a little semicircle. Does that domain look like it's things between -1 and 1? And the Desmos graph won't formally shade in the endpoints. But one thing you can do, if you can check that that point's on the graph, apparently it is, so -1's in the domain, so is +1. Nice. That feel pretty okay? Think you can do one on your own? Let's play the same game. The square root of x squared minus 2x plus 10. Compute for me that domain. as you're coming along. If you're getting to like a sticking point, then you can talk to each other. You can ask me a question. As any questions come up, go ahead and raise your hand and you won't feel alone. Cool, let's hear it. What's the domain?
All real numbers.
I hear an all real numbers. Do I hear a second? Cool. We'll talk through it in a minute because that's like an interesting answer. But for now, let's even just use a computer generated graph to double check. Alright. Yeah, that certainly looks like all x values are represented on that graph. So, let's go through the walk. So, if you want to find this domain, you need to figure out when that thing is bigger than or equal to 0. So you go and solve x squared minus 2x plus 10 equals 0. And what solutions did you get to that equality?
No solutions.
I hear no solutions. Right, so how many people use the quadratic formula? Cool, you got like a negative under that square root? And maybe for the sake of leading into what I'm going to talk about in a few minutes, that thing has no real solutions. Alright, so it has no real solutions. That tells you that if you were to graph y equals x squared minus 2x plus 10, there are no x-intercepts. So how did you go from there?
I saw that it was an upward opening parabola. So we'd have to, if it was, I don't know. I don't know how to explain it.
Yeah, so what you're coming close to is what a mathematician would call an argument by contradiction. If that turning point were below the x-axis, it'd have to crash through the x-axis, but there are no x-intercepts. So that's not possible. So it has to stay above the x-axis. Oh wait, but that means that y is always bigger than 0. So this thing's domain is all real numbers. Feel pretty good? Excellent. Alright, so what I want to do next is I want to emphasize like that pedantic point. Like it has no solutions, but really it does have some solutions. In fact, like you found the 2 solutions. What did the quadratic formula tell you the solutions to this should be? Well, let's see. So use the quadratic formula. You saw that the solution should be like negative b, so 2 plus or minus the square root of b squared minus 4ac all over 2a. Right, this is what the quadratic formula says. Oh, cool. So it has 2 solutions. They're those. They're 2 plus or minus whatever the square root of negative 36 means, all over 2. If you can invent a square root to negative 36, then there are your 2 solutions. So, let's think about what happens if you start allowing for numbers which are square roots to negatives. It's not a real number, because the square of any real number has to be positive, but it's something. Let's make up that something and see what happens. And in fact, advertisement for extra credit, this same game where you solve an inequality by solving an equality first, that's a philosophy you can use everywhere. Use it with stuff involving nested absolute values. There's an extra credit. So, if you want to think about solutions to these degree 2 polynomials, the reality is that every degree 2 polynomial equation, every quadratic, does have 2 solutions. as long as you allow for solutions that aren't like real solutions, but they're like fake solutions somehow. And as long as you are willing to count some solutions as double solutions. So as long as you put on some caveats, yeah, everything always has two solutions if it's a degree 2 polynomial. And let's like build up that subtlety by things that you already know. So there's a lot of examples where you just need to invent a new class of numbers to solve an equation. For example, let's suppose you only believe in the natural numbers, like the counting numbers. I can have 3 pigs. I can't have the square root of 5 pigs. So you only believe in counting numbers, but if you do, does that equation have a solution? I mean, it doesn't, right? I can only have like 1 pig at least, otherwise what am I talking about? But then if I have 1 pig and I add 2 more pigs, I have at least 3 pigs. So that equation has no solutions if you live in this world. But it does have a solution, right? What is the solution to that equation? 0. And this invention of a number called 0, which represents nothing, is an important development in the history of mathematics, being willing to think about that. And that leads you to, all right, so maybe you have to allow for negatives in 0. Where like, I don't know, like -3 pigs is like you owe someone 3 pigs. Maybe that's how you interpret it. But if you only believe in those, does that equation have a solution? No, if I had any number of pigs and I doubled the number of pigs, then I have an even number of pigs. 1 is not even. So that thing has no solutions. So again, the answer is no. But it does have a solution, right? What's the solution to that equation? 0.5. Or 1/2 if you like fractions. The point is it's a rational number. So-called because it is a ratio of 2 whole numbers. All right, cool. So, that gives you lots of numbers. It gives you any like decimal value that terminates or repeats. But it doesn't give you enough yet. So let's suppose that you believe in rational numbers now. Things that look like p over q with p and q integers and where you don't divide by 0. X squared equals 2. Can you solve that over just the rationals? The answer is no. Has anyone here already seen like the argument why you can't get a square root of 2 in the rationals? Cool. Well, if you want, there's one that's presented just after this in the notes. Go through it, come by, talk me through it, and you'll get some extra credit. Instead, its solution is, right, it's a real number. In fact, there are other adjectives you can put on it. You can call it an algebraic number because it solves a polynomial equation, but I think that's enough building in that direction for now. But let's carry on from there. Let's suppose you want to solve this equation. That's an equation that, like, seems reasonable to want to solve. X squared equals -1. Does it have a solution? Nope, a square is always positive. But it does have a solution. I'll give that type of solution a name. It's not a real number. It's like imaginary. I'll make it up. Feel pretty good? Nice. All right. So, with that like build up done, and people have seen some complex numbers in the past already. Nice. We're going to build it up fairly gently over the course of the rest of today. So what are the complex numbers? The complex numbers are what you get if you take all of the real numbers and invent one new number, which we will call the imaginary unit I. That number is chosen to be the number whose square is -1. So I've invented this new number and we'll just see what happens. So sometimes we'll just call I the square root of -1. And just for the sake of completeness, is anyone here going into a field that's electrical engineering adjacent? Yeah, okay. For an electrical engineer, I is often reserved for inductance. So they don't want to use I for the imaginary unit, so they use J. All right, cool. So what are complex numbers? Well, I should be able to add numbers together still, right? So a complex number well, like, I don't know, 7's a number. And if I is a number, then like 3i is a number. So I better be able to add those together, and that's still something that will count as a number. So a complex number is anything that can be written as a plus b, and that b is allowed to be multiplied by this complex unit. Groovy. Feel pretty good. So that means anything that looks like 7 plus 3i, maybe like 12 minus pi I, those things count as complex numbers. If that number b is 0, then a plus bi is just a. Oh, well, then it's a real number, if there's no imaginary part. If a is 0, then a plus bi is just a multiple of the imaginary unit. Those numbers I'll just call imaginary. So if you like, a complex number is anything that has like a real part and an imaginary part. Groovy. Feel pretty good? All right. So if these are things called numbers, we better be able to do arithmetic to them. So we better be able to add, subtract, multiply, and divide them. And add, subtract, and multiply will be pretty straightforward. Now let's just see what you think. If I were to just ask you 2 plus 3i plus 4 plus 5i, how would you want to add those together?
Combine like terms.
Let's combine like terms, where in this case like means either has an I or doesn't. So let's do that. You want to add these things together? Well, I would want this to be like 2 plus 4 plus 3i plus 5i. So far so good. 2 plus 4 is 6. If I have 3 i's and I add 5 more i's, how many i's does that total? 8i. Cool, so you add by just following your nose. Do the intuitive thing. For subtraction, same. You just need to, I guess, distribute a minus sign. So whenever you want to add two numbers together, just add the real parts and add the imaginary parts. If you want to subtract, do the same. Feel pretty good? Let's think about multiplying. And I think I'll go somewhat out of order. Let's go down to this example. 4 plus 3i times 2 minus 2i. If I want to ask you to multiply that, what idea would you want to use to do it? Well, I see like a sum times a sum. Whenever you see that, you should think about like what the distributive log makes you do. So I guess the acronym is FOIL. Multiply the first terms, outside terms, inside terms, last terms, but the actual order doesn't matter as long as you do all four. So let's see what you get. First term, 4 times 2, plus outside term, 4 times negative 2i, inside term, plus 3i times 2, last, 3i times negative 2i. So that's just what foiling tells you have to do. And let's just walk out each piece. 4 times 2 is 8. Plus, let's see, I see a negative in front of the 2, so that's 4 times negative 2 is negative 8i. Gesundheit. 3i times 2, well that's 3i's and then I double it, so that's 6i. And let's look at this last part. So maybe I'll pull that negative out. So it's negative. 3 times 2 is 6. And then I see I times I. Feel pretty okay? Oh, but what is I squared? Negative 1. I squared is negative 1. So, remember that I squared is negative 1, and let's use that. That'll be 8. May as well combine these terms while we're at it. Minus 8i plus 6i gives us minus 2i. All right, and that's plus 6 times, nope, minus 6 times negative 1, because I squared is negative 1. Feel pretty okay so far? All right, so if you want to multiply complex numbers, FOIL out the total. Remember that I squared is negative 1, and now let's just finish it up. What is that?
Negative 2i plus 14.
Negative 2i plus 14? Nice. Groovy. That feel pretty alright? So whenever you want to multiply complex numbers, FOIL it out. And then remember that I squared is negative 1. In fact, that's probably better than writing down a formula. FOIL it out, remember that I squared is negative 1. So let's do, I think, one more example here. If you know how to multiply things together, then you can raise things to a power. Because what does it mean to raise something to the 4th power?
Multiply it by itself 4 times.
Multiply it by itself 4 times. If you want to compute 1 plus I to the power of 4, it is 1 plus I, 1 plus I, 1 plus I, 1 plus I. That look computable? Yeah, maybe it takes a few steps. And I think the procedure I would endorse is first compute 1 plus I times 1 plus I. You can plug that in for both of the blue things and then go from there. And what do you think? If I just stand quietly for a little bit, will you tell me what that results in? Cool. Anyone want me to keep on talking right now? Nice. Then I'll be quiet for a bit. Once you have an answer, compare it with those around you. And then we'll come together. Cool, what are we getting?
-6.
I hear a -6. Do I hear a second for -6? Do I hear disagreement from -6? What else do I hear? I hear a 4. Do I hear a second for a 4?
-4.
I hear a -4. Do I hear other options?
4i.
I hear a 4i. Cool, I think there's cause to go through it. So let's do it. So step 1 was FOIL out 1 plus I times 1 plus I. I'll do that off in the margin. 1 plus I times 1 plus I. So, I guess to do that we gotta go and like FOIL it, right? So, first 1 times 1 is 1 plus I plus I. So that's plus 2I plus I squared. That feel okay? That agree with what people got? Nice. So I'm going to take that 2i and replace the thing that I underlined in blue with it, because it's the same. So this is equal to 2 times I times 2 times I. And maybe I'll put the parentheses there so it's more clear how this line came from the line above. But the parentheses don't actually matter, right? I'm just multiplying things together. All right, cool. So let's walk that out. So that's 2 times 2 times I times I. 2 times 2 is I times I. I squared, which is? All right, 4 times -1. Cool. Nice. People see if they have something else, what went wrong in their computation? Take a look at it, because like you can see a lot about how you think about things by seeing like what things went wrong. Nice. But in general, if you want to multiply, use the fact that you can FOIL these things out, and then use that I squared is -1, combine like terms, eventually simplify. Nice. What about division? That's like harder, right? If I were to just ask you, what's 1 plus I divided by 3 minus 2i? Well, it's not like I can FOIL anything out. You can distribute the division so you'd have 1 over 3 minus 2i plus I over 3 minus 2i, but it's not like anything simplifies there, so that's not like useful. So I think here's the general plan of attack that I'd want to make. The denominator is complicated looking. And usually when you see the denominator being complicated looking, you want to think about like, what do you need to multiply and divide by to make the denominator simple looking? Right, like 5 divided by √2, if you want to think about that, you multiply and divide by √2. The reason to do that is √2 times √2 is 2, now the denominator is nice looking. I want to do something like that here, so I guess first I need to figure out what I can multiply the denominator by to make the denominator nice looking. And hold on to that thought. I will now compose a definition. For any complex number, a plus bi, I will define its complex conjugate. I'll denote it by drawing a line on top. Whenever I draw a line on top of a complex number, that indicates the complex conjugate. It's given by a minus, I guess it's ib, so I'll say ib instead of bi. You take the imaginary part and you put a negative sign in front. That is the complex conjugate. And here's why the complex conjugate is interesting. Let's walk it out in an example. 4 plus 3i multiplied by the complex conjugate of 4 plus 3i. So let's walk that out one step at a time. I'm going to leave the 4 plus 3i alone. for now. What's the complex conjugate of 4 plus 3i? Excellent. The complex conjugate, you just stick an extra negative sign out in front of the imaginary term. Oh, cool. So now that's something that we can like FOIL out, right? Let's do that. We'll wind up getting an answer that is interesting. So 4 times 4 is 16. 4 times minus 3 is minus 12i. 3i times 4 is 12i. 3i times negative 3i, well, there's enough stuff there that I'm just going to write it out. It'll be negative 3 times 3 is 9 times I squared. Did I do at least that stuff correctly? All right, now let's just look at what you see and tell me what looks nice and helpful.
The 12 eyes are going to cancel out.
12 i's cancel out. That's nice. Anything else nice you see?
The I squared makes the negative 9 positive.
Nice. I squared is negative 1. So I can like cancel the I squared with the minus sign in front of the 9. Oh, cool. What does that leave you with?
16 plus 9.
Which is
25.
25. Cool. And in fact, there was nothing special about 4 and 3 that made that happen. Whenever you multiply a complex number by its complex conjugate, the imaginary terms will always cancel. And in like the last term, you'll always see minus I squared. So you can always just walk that out, but you can also just can the result. A plus bi times a plus bi squared will always be a squared plus b squared. Just like what happened in the previous example. A was 4, that's why I had a 16. B is 3, that's where the 9 came from. Cool. The point is, if you see a complex number and you want to turn it into a real number, one way to do that is by multiplying by the complex conjugate. Oh, nice. So that tells you what you need to multiply and divide by. If you see division by a complex number, and you want to realize it is something that's easy to understand, multiply and divide by the complex conjugate. So let's do that in this example. 1 plus I over 3 minus 2i. Step 1, multiply and divide by the complex conjugate of the thing on the bottom. What's the complex conjugate of 3 minus 2i?
3 plus 2i.
3 plus 2i, because a double negative will be positive. So let's do that. That will leave me with 1 plus I divided by 3 minus 2i multiplied by 3 plus 2i divided by 3 plus 2i. And I think I have enough space to play this game in line. So let's see. I guess now I actually have to do the walk of like foiling out the top and the bottom and simplifying. Although, do I actually have to foil out the bottom at all? You know what the bottom's going to be. What will the bottom walk out to be?
9 plus 4.
9 plus 4. 3 squared is 9, plus 2 squared is 4, which is 13. Nice. So we already know what the denominator is. It's division by 13. I don't have any such trick for the numerator because I didn't pick this thing to multiply and divide by to make the numerator nice. I just know the numerator is not going to get much worse. So let's just FOIL it out and see what it is. Should I do or should I wait for you to do? Should I do the foiling? Cool. Then I will. 1 times 3 is 3, plus 2i, plus 3i. I times I is I squared, so that's minus 1 times 2. Minus 2. And one of those i's doesn't look I-ish enough. There we go. Alrighty. So now, you already told me that the bottom is equal to 13. So let's replace the bottom with 13. Combine like terms in the numerator. What is it?
1 plus 5i.
I hear a 1 plus 5i. Cool. And in some sense, there's a perfectly good simplified answer. If you were to report to a human being that this result of division is 1 plus 5i all over 13, great. Some of the webwork problems will be like picky and say, no, I want you to tell me what the real part is and what the imaginary part is. So I guess to do that, you could distribute the division. That's the same thing as 1 divided by 13 plus 5 divided by 13i. Groovy. Feel pretty okay? Nice. And with 5 minutes left, I think the choices are, I go back to remembering why we're doing all this shit with complex numbers, or there's time for one more example of division. People think they benefit from one more example of division? Then let's spend time on one more example with division. We're doing okay schedule-wise anyway. Oh, by the way, you should also be able to take square roots of complex numbers, right? Right? Otherwise, we're losing too much. Extra credit, take the square root of a complex number. It's at the end of this section in the notes. Anyway, there's a bit of division to do. I think the options are, like, I be quiet for a bit, you do it, you compare with those around you, when we come together, or, like, I keep talking. Do I keep talking? Cool. Let's play the game. So I want to do 4 minus I over 3 plus I. So, step 1, when computing a complex fraction, I need to turn the denominator onto something that's less hard to work with. The numerator will become more complicated, but that's okay. What should I multiply and divide by? Say louder. 3 plus I. No, 3 minus I. I need to multiply and divide by the complex conjugate. So, 4 minus I over 3 plus I. Right, I want to preserve this equality, so I better like write down the thing that I already have, because I just don't want to change it. Multiplied by 3 minus I divided by 3 minus I. Cool. Alright. And from there, what do I need to do? I guess I need to like expand out the numerator, expand out the denominator. I know that the denominator should be real when I'm done with this. And then combine some like terms and call it a day. So let's do that. So I guess start by foiling out the numerator. 4 times 3 is 12. Outside, 4 times minus I is minus 4I. Inside, minus I times 3 is minus 3I. Well, gosh, there are too many negative signs, so that's too many things to do at once. Double negative will become a positive I squared. I screw anything up yet? Things look okay? All right. Denominator. On the one hand, like maybe you just know by glancing at it that it should be 10, but let's actually do it. 3 times 3 is 9. Outside is minus 3i. Inside is plus 3i. Last is minus I squared. Feel pretty good? I know like the hard walk's done, now it's like combined like terms. So you look at the numerator, how big is the wheel part? I think it's 11? Yeah. And I like color coding. 9 plus I squared, that's 9 minus 1. So that's 11. Minus 4i minus 3i is minus 7i. Denominator, the whole point of this game is that the complex bit, the imaginary bit cancels. And you're left with 10. Which is what you knew it had to be to begin with. Nice. So, I guess if you want to write it... Ooh. That time it worked out pretty okay. Finish the example right at the end of the hour. And if you don't want to put it as decimals, if you like fractions, put it as fractions. Just, I wanted to remind you that decimals exist. Neato. So, let's see. Class meets normal format. Take a look at things like the web walk and the open-ended, because tomorrow is like the last chance to ask questions before it's due. So.